Should imbalanced datasets always be preprocessed for decision trees? Imagine you're trying to teach a computer to tell the difference between spam and regular emails. Sometimes, most emails are not spam, and only a few are. This is called an imbalanced dataset. Now, if you use a decision tree to learn from this data, it might get lazy and just guess the most common class all the time. That means it could miss the rare but important spam emails. So, the question is, should you always fix this imbalance before training your decision tree? Decision trees are popular because they split data into groups based on features, trying to make each group as pure as possible. But when one class dominates, the tree tends to ignore the minority class because splitting doesn't improve the purity much for the less frequent group. This can lead to poor detection of the minority class, which might be the most important one in some cases, like fraud detection or medical diagnosis. To handle this, you can use different preprocessing techniques. One way is to oversample the minority class, which means copying or creating new synthetic samples so the classes are more balanced. A common method for this is called synthetic minority oversampling technique, or SMOD, which generates new data points similar to existing minority samples. Another approach is undersampling the majority class, which involves removing some of the common class data to balance things out. Sometimes, combining both oversampling and undersampling gives the best results. Another strategy is to make the decision tree more sensitive to the minority class by assigning higher costs to misclassifying those rare examples. This is called cost-sensitive learning. It makes the tree pay more attention to the minority class during training. You can also change how the tree splits data by using different criteria, like Hellinger distance, instead of the usual information gain or Gini index. These alternative measures can help the tree better recognize the minority class even without changing the data. You can also modify the decision tree algorithm itself to include class weights. This means giving more importance to the minority class when choosing where to split. It helps balance the influence of each class during the learning process. When evaluating your model, accuracy alone can be misleading if the data is imbalanced. Instead, look at metrics like precision, which shows how many of the predicted positives are correct, or recall, which shows how many actual positives you caught. The F1 score combines both, giving a better picture of performance on the minority class. The ROC AUC score is also helpful because it measures how well the model distinguishes between classes overall. In real-world applications like detecting fraud, diagnosing diseases, or predicting responses to marketing, handling imbalanced data is very important. Tools like ChatGPT and AI plugins can help automate the pre-processing steps and select the right metrics. This way, models become fairer and more accurate in recognizing all classes. So, in most cases, especially when the data is heavily skewed, pre-processing or adjusting the decision tree is a good idea. It helps prevent the model from ignoring the minority class and ensures better overall performance.